Hello everyone. In today's lecture, we will move on with the next topic in airport engineering, that is runway design. Runway design is one of the important topics. As I told you, as you learn more about airport, it will be much helpful for you as a civil engineer to find high profile jobs in construction industries. So that is the major importance of airport engineering. So in this prospect, we will start with our next topic, that is runway design. So runway design, coming to the runway design, our first topic is orientation of runway. So in order to give some introduction about the runway design, the number and orientation of runways plays an important role in the overall arrangement of various components of an airport. See, basically runways are nothing but, you can observe in the background picture here, the runways are nothing but the ways which are used for the purpose of landing the aircraft. So the slide also I have made particularly for that purpose in order to show the runway. The number of runways will depend on the volume of air traffic, while its orientation will depend on the direction of the wind and sometimes on the extent area available for the airport development. This is how the runway design is decided. In general, the arrangement of runways and the connecting taxiways should comply with the following conditions. First one, to avoid delay in the landing, taxiing and takeoff orientations, and to cause the least interference in these operations. The second one is to grant the shortest taxi distance possible from the terminal area to the ends of the runways, to make provision for adequate taxiways so that the landing aircraft can leave the runways as quickly as possible and follow routes as short as possible to the terminal areas. Next, to provide adequate separation in the air traffic patterns. So in this chapter, the main aspects connected with the runway design will be described. So in that we will move on to our first topic, that is the runway orientations. What are the prospectus on which the runway orientations are determined? What are the preliminary informations required? The first point is preliminary informations required. It is necessary to collect the following data before deciding the orientation of a runway. That is, what are the data that we have to collect here? Maps of the area in the vicinity of the airport showing contours at suitable intervals, and the second one is, the second data that is required is the records of directions, forces and duration of the wind in the vicinity and fog characteristics of the area for as long as period as possible. The second one is headwind. The second characteristic is headwind. The runway is usually oriented in the direction of the prevailing winds. The headwind indicates the wind from the opposite direction of the head or nose of the aircraft while it is landing or taking off. The orientation of runway along the headwind grants the following two advantages, that is, the duration during landing. During landing, it provides a braking effect, and the aircraft comes to a stop in a short length of the runway. During takeoff, it provides greater lift on the wings of the aircraft. Thus, the landing and takeoff operations takes place in the shorter length of the runway due to the headwind than what it would have been if the landing and taking off were in the direction of the wind. Headwind is nothing but the wind which is facing the aircraft, the wind which is blowing in the opposite direction. The reduction in length of the runway may be about 10% due to the headwind, right? This is about the headwind. Next, moving on, our third characteristic is crosswind component. It is not possible to get the direction of opposite wind parallel to the center line of the runway length every day or throughout the year. For some period of the year at least, the wind may blow making some angle theta with the direction of the center line of the runway length as shown in the figure. If we So I don't want to discuss this crosswind characteristics with the help of a diagram. It is not so crucial. Just know the know the terminology, that is crosswind component. Next, moving on, the wind coverage, the percentage of time in a year during which the crosswind component remains within the limit of 25 kmph is called as the wind coverage of the runway. Wind coverage of the runway. The orientation of the runway should be such that the minimum wind coverage of about 95% is obtained. For busy airports, it is possible to obtain wind coverage up to 98% or even 100%. Fifth one is the windrows. For the airport, the average wind data of 5 to 10 years period are collected and represented graphically in the form of a chart known as windrows. The diagram is given the name windrows because of its irregular shape and resembling arrows. The study of windrows helps in determining the most suitable orientation of the runway. It is also a useful device for estimating the runway capacity. So we are going to discuss this runway concept in the next slide. So I have been the table 4.1 gives the details of typical wind data for an average of 5 years. It is assumed that the duration of wind for any one direction covers an angle of 22.5 degree as shown in the figure. So we'll move on to our next slide. So in this slide we are going to discuss more about the windrows diagram, right? We are going to discuss more about windrows diagram. So for us, in order to determine the wind, we in the previous slide we have looked upon what is windrows diagram. So in this slide we will study about how we are going to draw a windrows diagram. So in this particular slide you can see a tabular column which consists of the directions, which includes the 16 directions, and the percentage of time, duration of wind. So in the percentage of time and duration of wind is divided into three different components, that is the wind blowing 6 to 25 kilometers per hour, the wind blowing 25 to 50 kilometers per hour, and 50 to 80 kilometers per hour. That is, we have characterized the percentage of wind which is blowing mostly for about 5 years. Let us consider for 5 years time period, the wind blowing, the average wind blowing in the particular direction at a particular speed is characterized in this particular slide, and it is noted down in the form of percentages. So finally, the total percentage of wind blowing in each direction is summed up as at the end of the total. So let us look into a windrows diagram. The windrows diagram is can be plotted into different types. So we are going to learn about one type of plotting windrows diagram. So in this, the type 1, the windrows diagram as shown in the figure 4.3, you can observe here the figure is shown here as 4.3. The figure shows the windrows diagram of this type, that is type 1. This figure is a type 1 type of windrows diagram. The radial lines indicates the wind directions. These radial lines indicates the wind direction, and each circle, you can observe the concentric circles here. Each circle represents the duration of wind to a certain scale. From the wind data from table 4.1, the total percentage of wind blowing in north is 6.10, and accordingly this point is marked along north direction. So this 6.1 is marked in the north direction, you can observe here. Similarly, all other values are plotted and then joined by the straight lines. The best direction of runway is indicated along the direction of the longest line on the windrows diagram. Longest line in the windrows diagram. You can observe here. This is the longest line in the windrows diagram. In the figure 4.3, west northwest, that is west northwest, east southeast, east southeast is the best orientation for the runway. This type of windrows diagram does not consider the effect of the crosswind component. So this is a simple type of windrows diagram. So here what we are going to do is we are going to draw certain concentric circles, concentric circle which represents these scales, that is 6 to 25, 25 to 50 and 50 to 80 kilometers per hour. So the concentric circle are plotted to a certain scale. If you observe this particular windrows diagram, the scale is taken as the first concentric circle is drawn to a scale of about let us assume the 3. The scale is 3 here, 3. So if you want to plot a particular percentage on this particular direction, let us consider we have a northern direction. In the northern direction, the scale that is a particular percentage wind blowing is 6.10. So if you observe here, the 6.10 is plotted in the northern direction to the particular scale. You can observe here the 6.1 comes in this region of this windrows diagram. The same thing is plotted here, 6.10. Hope you have understood the concept of plotting the windrows diagram. It is a very simple method of plotting. Just draw 3 concentric circles on within the concentric just draw 3 concentric circles to a certain scale. Draw this concentric circle to a certain scale. Just plot these values on the concentric circles to a certain scale, and just the longest scale, the longest line represents the direction of a runway. So this is how we are going to plot a windrows diagram. So let us move on to our next concept of the runway configurations. So runway configurations. In the runway configurations, we are going to look into several classifications. That is basic runway length of the basic length of the runway. So what are we going to learn in this basic runway length? The basic runway length, the maximum or minimum runway length that needs to be provided. That is what we are going to learn as per the ICAO classifications. The length of runway based on the following assumed conditions is known as the basic runway length. First one, no wind is blowing on the runway. The aircraft is loaded to its full loading capacity. So we are going to make certain assumptions. The airport is situated at a sea level. There is no wind blowing on the way to the destination. The runway is leveled in the longitudinal direction, or in other words, it has zero effective gradient. Next, the 6th point is the standard temperature is maintained along the way. The last point is the standard temperature of 15 degrees centigrade exists in the airport. The manner in which an airport actually performs the landing and takeoff will decide to a large extent the length of the runway. So this is about the basic length of the runway. Next, moving on, the corrections to runway length. What are the corrections? So we are assuming certain conditions. Let us consider if these assumptions are not validating at a particular runway. So in order to meet these assumptions, we are going to apply certain corrections as per the ICAO and FAA recommendations or specifications. To get the actual length of the runway, the following 3 corrections are to be applied to the calculated basic runway length. Let us assume we have calculated certain basic runway length. If the runway length is not meeting our requirements, we are going to apply certain corrections. The corrections for elevation. The first one is the correction for elevation. As per the recommendation of ICAO, the basic runway length should be increased at the rate of 7% per 300 meter rise in elevation. This is a very important point for adapting for calculation of problems. So in this, what is the type of corrections we are applying for elevation? Let us assume if we have not got the elevation at the sea level, we have to apply correction for the elevation. As per the recommendations of ICAO, the basic runway length should be increased at the rate of 7% per 300-meter rise in the elevation of airport above the mean sea level. The correction is required because the air density reduces as the elevation increases, which in turn reduces the lift on the wings of the aircraft. Thus, the aircraft will require more ground speed to rise to the air, and for achieving more speed, the longer length of runway will be required. In order to achieve more speed, the longer length of runway is required. Next, correction for gradient. As the gradient becomes steep, more consumption of energy takes place, and longer length of runway will be required to attain the desired ground speed. The ICAO does not give any specific recommendations for the increase in length due to the effective gradient. The maximum difference in elevation between the highest and the lowest points of the runway divided by the total length of the runway is known as the effective gradient. According to FAA, Federal Aviation Administration of USA, the runway length after being corrected for elevation and temperature should further be increased at the rate of 20% for every 1% of the effective gradient. So this is the correction for gradient. Next, third point is correction for temperature. The rise in airport reference temperature has the same effect as that of the increase in its elevation above mean sea level. After the basic length is corrected for the elevation of airport, it is further increased at a rate of about 1% for every 1 degree centigrade rise in the airport reference temperature above the standard atmospheric temperature at that elevation. The airport reference temperature is worked out by the following expression. The airport reference temperature is equal to T1 plus T2 minus T1 divided by 3, where T1 is equal to monthly mean of the average daily temperature for the hottest month of the year. T2 is equal to monthly mean of the maximum daily temperature for the same month. The standard temperature at the airport site can be determined by reducing the standard mean sea level temperature of 15 degrees at the rate of 6.5 degrees centigrade per 1000 meter rise in elevation. Note, the ICAO recommends that if the total corrections for elevation plus temperature exceeds 35% of the basic runway length, the specific studies at the site by model tests should be carried out before finally adopting the runway length. If 35%, if the correction is exceeding more than 35%, some basic test has to be conducted at the site. This is what the corrections refers to. Let us directly move on to the problems. There are certain problems related to the airport runway length. These are very simple problems. These are the standard methods. It is very easy to follow. You have about 1, 3, 5, 6 problems or 7 problems. These 7 problems are almost one and the same, almost similar to each other. If you just understand one problem, it is enough. So I have taken up explanation of a second problem. So in this problem, the length of runway at sea level under standard condition at zero gradient is 1500 meters. The airport site is at elevation of 900 meters. The reference temperature is 20 degrees centigrade. The proposed runway permits ascending gradient of 0.5%, designing the longitudinal profile of runway. So solution for this: correction for elevation. The basic length of runway is to be increased at a rate of 7% per 300 meter elevation above mean sea level. So this, if you understand the concepts which I have explained in the previous slide, that is similar to the, if you understand the theory part, it is very easy. That is the basic length of runway is to be increased at a rate of 7% per 300 meter elevation above mean sea level. Correction for elevation is equal to 7 by 100 into 900 by 300 into 1500. If you observe here, the airport site is at an elevation of 900 meters. So we have to apply correction for this 900 meters. So if we apply corrections, we have to increase the runway length by about 315 meters. The length of runway after correction of elevation is equal to 1500 plus 315 is equal to 1815 meters. Correction for temperature. Reference temperature is equal to 20 degrees centigrade. Standard atmospheric temperature at mean sea level is equal to 15 degrees centigrade. Next, standard atmospheric temperature at given elevation is equal to 15 minus 0.0065 into 900 is equal to 9.15 degrees centigrade. So this is how we are going to apply correction for temperature. Rise in temperature is equal to 20 minus 9.15 is equal to 10.85 degrees centigrade. Applying correction at a rate of 1% for every 1 degree centigrade. Correction of temperature is equal to 1 by 100 into 1815 into 10.85, which is equal to 196.93. say it is approximated to 197 meters. Corrected length. The new corrected length due to temperature is 1815 plus 197, which is, so previously it was 1500. It has been increased by 315 meters due to the correction which we applied for the elevation. So due to the temperature, we have increased length of about 197. So now after applying correction for temperature, we have to provide a runway length of 2012 meters. Next type of correction what we are applying is correction for gradient. The effective gradient is equal to 0.5%. This has been given in the problem itself. The proposed runway permits ascending gradient of about 0.5%. Applying correction for the effective gradient at the rate of 20% for each 1% effective gradient. The next, therefore, the correction for gradient is equal to 20 by 100. That is, we are converting it converting it into meters. That is into 2012 into 0.5 divided by 1, which is equal to 201.20, say 202 meters. So actual runway length is equal to 2012 plus 202, which is equal to 2214 meters. Check. So whatever the corrections which we have applied, it should not exceed more than 35%. So in order to check the percentage increase in the length of the runway, we have to check the corrections. The total correction for elevation and temperature is equal to 512. The percentage increase is equal to 34.13, which is less than 35%. Therefore, according to ICAO, this should not be more than 35%. Hence, okay. Thank you. Hope you have understood the concepts.